Michael Davies. I'm a research analyst with Green Econometrics. Here we're talking about something large, far-reaching, and the foundation of our future, and it's EV charging. So what set the stage for this? We have the bipartisan National EV Infrastructure Program, and the funding is soon approaching. And it's a $5 billion, 5-year program that calls for the installation of 500,000 EV charging stalls that will be dispersed along the interstate system, 50 miles apart. And it comes with some implications for the grid. So for one, EV charging is energy intensive and will impact demand. And with that, renewable energies are going to play an increasing role in supporting that demand. But renewables come with their own set of complexities to the grid itself. And we'll get into that. The other side of it is these are long distance transmission lines that need to support high intensity endpoints. That further complicates the management of the grid. And lastly, we want to talk about the support coming from distributed energy resources, namely smart devices that will help manage the resiliency and the stability of the grid. And with that, we have basic implication of the EV charging. And if we look at the demand that will arise from home charging, it's not that critical here. For one, these will be level 2, so relatively low voltage, low amps. It will increase demand at the home if someone does install an EV charging at home. But as far as the grid is concerned, these things are not that impactful, we'll say. What we want to look at, though, is, what does it mean for the high capacity fast charge EV systems out there? These are much larger. In fact, these are very large systems and will require considerable thought to manage the grid. So what we want to look at is then, where does the demand come from? If we look at this chart here, we see that energy demand is being met through fuel sources. Coal and oil are on the waning factor here. Gas and renewables are certainly expanding their role in supplying electricity. Nuclear is relatively flat. It's got its own set of complexities. Coal and oil, because of the high carbon output, are less desirable. And if we take a step and look at the EV charging infrastructure, we want to come up with a framework to understand how energy intensive are these devices. These are EV charging stalls. And so Tesla has like 175 kilowatts. We have Electrify America has stalls out there that are 350. So the bipartisan National EV Infrastructure Program is calling for a minimum of 150 kilowatts in a stall. So if we put that in a framework, you're essentially looking at a building in a box, if you will. The EV charging measurement of kilowatts per square foot is significantly larger than that of data centers. Even though data centers and crypto mining may consume more energy than does the EV charging, because these things are dispersed in long distance and you have long transmission lines, the energy intensity is that much more demanding on the grid itself. And so with that, we'll take a step back and look at what it's going to take to better manage the grid and why frequency and reactive power play an important role in the stability and resiliency of the grid itself. So let's look at frequency. Frequency is in tandem with voltage. And it's required to have a stable input. You have hydro and gas turbines that rotate at a constant speed that maintain a 60 hertz frequency, which is used in North America to provide long distance transmission stability. Coming to the end users at that frequency is important. Fluctuations in frequency create imbalances where voltage drops could be rather dangerous and could impact not just the grid, but a lower voltage. You're having increasing amps, which will heat the cables, heating the equipment, and that could damage both. Maintaining that frequency with renewables is a challenge because renewable energy does not have that inertia to maintain a 60 hertz frequency. Therefore, you need smart converters from DC to AC to inject into the grid and provide you with the means of stabilizing the frequency of that power coming in. Changes in demand, either from the load side or injection of more power into the grid, are going to create imbalances, and you're going to have to manage this end to end. The other factor is reactive power, which is a strange animal in and of itself, because you have this magnetic field that actually helps inductive motors start because it provides a means of initiating that start, and it paves the way by providing a way to assure voltage at long transmission lines. You need the reactive power to provide an easier conduit for the flow of electricity. And too much reactive power is very inefficient. And again, when you have changes in reactive power, you have an impact on voltage, which again, you get voltage drops that can be damaging to equipment and the power lines. So it's a difficult balance to manage each of these elements. So bottom line, what we're looking at here is the importance of smart distributed energy resources to support both renewables coming into the field and the ability to better manage the stability and resiliency of the grid itself. Thanks.